2.1 Ethernet layer. After verifying and optionally zeroing the Ethernet checksum and applying a MAC address filter, the NIC copies the packet to the system's memory via DMA, direct memory access. Then it notifies the operating system via an interrupt and indicates the location of the packet data. Okay, so comprehension question. What does the NIC do with the packet it has received? And how does the NIC let the operating system know there's a packet for it to look at? With this, the operating system can allocate an SK buff. Now the kernel inserts metadata into the SK buff, like the protocol field, Ethernet in this example, and the receiving interface, and the packet type, in our case, IP. So our next question is, what does the kernel do after the interrupt and location of the packet, it should say, is sent to it, the kernel, by the NIC? Looks like the kernel is inserting metadata. Alright, so at this stage, the kernel knows the start of the Ethernet header, so it sets the MAC header field to the beginning of the SK buff. Finally, it removes the Ethernet header from the SK buff before it passes it further up the network stack. Next, the packet arrives in netifReceiveSKB. The function clones skbuff and forwards it to the virtual tap interface. The tap interface enables communication between virtual machines and the host within the same network. Another important case here is forwarding VLAN tagged packets to the VLAN interface. Furthermore, when the interface has a physical master, that is, it is a virtual interface or part of a network bridge, Rx handler steals the packet. Rx handler also sets the network header field of the SK buff. Finally, it calls the IPv4 protocol handler function IP receive. Alright, IP layer. The Ethernet layer passes the packet to the IP layer via the function IPRCV. Again, IPRCV inspects the MAC address and drops foreign ones. Then the version, length, and checksum fields are verified. Next, the function sets the transport header field of the SK buff. It also applies netfilter's pre-routing rule. It implements the filter by forwarding the packet to the NF-INET pre-routing hook. The hook gets a pointer to the IPRCV finish function that it calls after completion. If a network layer master device is registered, it passes the SK buff to its handler. It calls IP route input noref, which reads the IP header from the SK buff. Next, the kernel processes IP options via IPRCV options. Afterward, it calls the previously selected routing function via DST. What do you guys think? Is that for Destiny? Input. So there are three options for routing a packet. Number 1, IP forward. This function activates for packets not addressed to the current machine. It proceeds by forwarding the packet without additional processing. Number 2 is IP local deliver. If we are the final receiver of the packet, localhost, the kernel does not forward the packet but passes it up the networking stack. And then number 3 is IP MR input. Okay, just kidding. IP MR input. This function is for multicast packets, that is, addressed to a multicast address. So what is that for? Multicast route? As we are mainly interested in how a packet is handled at the final receiver, taking all layers into account, we continue with IP local deliver. Most importantly, this function takes care of IP fragmentation by calling IP defrag, queuing packets until receiving all fragments. Afterward, the event NF-INET local IN triggers, which in return calls IP local deliver finish, stripping the IP header from the SK buff. Finally, it passes the packet from the IP to the TCP UDP layer via the DST input function to the TCP v4 receive. Or is that a typo? Anyways, it determines the corresponding protocol handler by inspecting the header pointing to the SK buff. Transport layer. Now we inspect the counterpart of the egress TCP and UDP functions, starting with TCP. First, the segment arrives at the transport layer function TCP IPv4 receive with the SK buff header pointer moved to the start of the TCP or UDP header. Then it validates the transport header via PSKB may pool. validating the TCP checksum. As before, it removes the TCP header from the SK buff. To pass the packet further, it locates the corresponding TCP socket via inet lookup skb. It writes the packet to the socket receive queue and signals that new data is available, for example via SIG-IO or SIG-URG. This notification mechanism allows for efficient polling of sockets. As for the egress, the kernel maintains a TCP state machine during packet processing. For example, it processes no new packets for TCP connections terminated via a TCP closing. We briefly highlight two important cases during processing: TCP new SYN receive and TCP time wait. TCP new SYN receive means that there is a new connection. In this case, the kernel refuses connection at TCP level via TCP filter. So the question is, when does the kernel refuse connections at the TCP level and how? Furthermore, there is a slow and a fast path. The slow path contains more error checks and lookups. In contrast, the fast path is optimized for speed, not allowing introspection and traffic analysis. With the slow path, we wait until the state machine is at TCP established in TCP v4 do receive. Once updated, TCP v4 do receive calls TCP receive established, which processes packets both in the fast and slow paths. It also validates that sequence numbers are ascending. The fast path copies the packet directly to the user space. The kernel always tries to use the fast path if possible, but when, for example, establishing a TCP connection, this not possible since the kernel has to track the new connection. After handling the TCP state machine and choosing the path, the kernel enqueues the packet into the socket queue so that the user program can read it. Since TCP is very complex, covering further aspects is beyond this paper's scope. However, 7.10.11 describe it in more detail. UDP. Compared to TCP, the implementation of UDP is less complex. It starts with UDP receive message, called via DST input, in the IP layer. First, the function calls skb receive UDP to read the datagram from the socket with a previously calculated offset. In particular, it continuously tries to read a SK buff from the socket, eventually stopping when a new UDP datagram arrives. The checksum of the datagram is then validated. Then the function copies the destination IP and UDP port to map the datagram to the correct socket. Consequently, it consumes the UDP datagram via skb consume UDP. Finally, it adjusts the peak offset, handles reference counters, and frees the SK buff via consume stateless skb. Right, in the next video, we'll start with the socket layer.